So now the keystones we just unraveled that you did a really actually we got one more to do, but the keystones we unraveled on the last one is that you understood the y-intercept, the horizontal asymptote, the vertical asymptote, the x-intercept, and pragmatic usage of tables. Right? You understood the behavior of this graph and how it relates to the other one that even when the horizontal asymptote is on the x-axis. These are very powerful thoughts. You made one, and you understood a new keystone. You can never have any function cross through the horizontal asymptote or vertical asymptote. So now we're moving on to this one. Explain to me the graph you did here. Let's go ahead and do this problem real quick.
So numerator 0 is -1 because you have to find your x-intercept, and you have to equal your numerator to 0 to find the x-intercept, aka your root. So once you equal x plus 1 equals 0, you get -1. Okay, and I graphed it on the, if you can see the red point here.
What did you do though? Tell me. What keystone did you learn on the last one? Yeah, we got a problem, right? Hey,
I see.
but you already solved. But look, now you're reinforcing the keystone. Sometimes it takes two punches.
And it cannot go through the asymptotes.
But you did get the horizontal asymptote correct. Very good.
Yeah.
That was x equals 0. Very good job.
The vertical asymptote is 0 because if you get on to get the vertical asymptote, you get on the 0.
We just can't have that. Yes, you did. Yeah. That is also. So your vertical asymptote was division by 0 there, x equals 0.
It will be negative infinity, comma 0, union 0, comma infinity. And your y-intercept is going to be undefined because if you plug in 0 for x, 0 plus 1 is 1. And okay, you plug in x to the 0 to the switch, it's going to get 1 divided by 0, and you cannot do that. So that's undefined.
Right. Oh, good job. That's a new concept you just picked up on. Very good.
Well, I remember that from algebra 1. So that's how I remember.
Well, good. I mean, that's solid thinking.
Yeah, in order to find your, of course, to find your y points, you have to plug in whatever x is. So -2 plus -2 plus 1 is -1, and -2 squared is +4. So it's -1/4.
Right.
And I believe that says -1/2. Yeah, it should say. Yeah, that says -1/2. So if you put -1/2.
Good. So okay, let's redo this. So at -1/2, right? Let's kind of, I'm going to go through this. So you did -2 and you got -1/4. That's good.
I know what I did wrong.
Good.
Because I mean, logically speaking, these two cannot have the same y coordinate.
Not only that, but at -2 you got -1/4. So what does that tell you about your graph over here on the left-hand side? That tells you that because you crossed the asymptote here, which you can't do. So that means that let's go ahead and regraph this together, right? You and I. You tell me what to do as we go along.
Okay, now my question is, I hope operator notation did not get the best of me, because -1/2, I put it in, -1/2 plus 1 is +1/2.
So you know your domain and your long run behavior, of course, now.
Yeah.
And now, since we have the behavior of 1/x, right? Let me ask you, since we know it looks like 1/x behavior, exactly, right? We are still going to put in points, but we do know that the graph needs to look something like that original parent function, right? It might be different. You might have an intercept, in which case we do. We may have one. I haven't looked. Yeah, x-intercept is -1. Okay, wait a minute. If you plug in 0 for y, sorry, no, that does say that x is -1. But what about your horizontal asymptote?
My horizontal asymptote is 0.
I know that. I was thinking out loud. Um, let's just negative. Oh, wait. If you plug in -2, let me try this. I'm sorry. Let me get my brain into this. So -2 over that and -2 squared. Yeah, that's -1/4, all right. So we're encountering a problem. Can you see?
Try -1/2.
Because if we plug in -1, or if we solve for the x-intercept, right?
Right.
There's something unforeseeable. I don't know why it's just passing through there. Because we can see that it deteriorates as you become more increasingly negative. So that does validate the horizontal asymptote being 0. So this is a very strange situation. Let me go ahead and actually, this is very uniquely strange. Because why would it be? It may not be. Wait, and we're just going to have to reset this. Sorry. It may not be 1/x behavior. But if this one's very problematic. Probably is. It's just that, let me go ahead, because I'm encountering an issue. You shouldn't have an x-intercept. Let me look at the graph. Give me a second. What do we have here? X plus 1/x². Yeah, give me a second. I'm going to sound like I have no idea what I'm talking about, but I do. But here I'm kind of a little bit perplexed myself. Let's go ahead and I'm going to define a function. Let's see, h of x. Let's do g of x maybe. What we have here, we're just going to put in here x plus 1 divided by x squared. And just to make sure that it's typed in right. And it ain't. And so let me fix that. Good. So now I'm going to plot this guy, this gal. And we can see, yes, as suspected, the behavior definitely isn't 1/x. And the vertical, how do I put this? Because it seems like I'm going back on my word here. And this is what distinguishes a teacher from a tutor. I'm going to let you know right now, is that we put the tough ones on here. They don't even seem like they look tough, but hey, and let me explain what's going on. So a keystone here is not broken. It's been bent. And let me explain. On the last one, I said we can never have any function cross. That's not entirely true. So I apologize. I've made a mistake. It can, but it will never cross so much violently like that. Does that make sense? If you look on slide 9, you'll never have anything cross an asymptote in such a way. They'll never cross like that. You know what I mean? They tend to flatten out towards them if they do cross them, and they barely do.
Yeah, look.
A little bit of quantum tunneling going on with this one.
That way.
Right. So it does go through the asymptote, unfortunately. It does go through the horizontal asymptote. But when it does, it may be suspect to questioning because, again, if I take the limit of this, and that's one of the things that I haven't taught you yet because it's really a pre-calculus technique. But if you take the limit as x goes to -infinity or just anything, what we can do is we can just look at this function. And one things we do as mathematicians to, instead of making a comparison like up here where you get, because we really have, but it's even behavior because of the squared, because of the x squared is in the denominator. And if it's x squared in the denominator, that dominates the behavior of the rational function. So then right here, what we can say is we can divide everything by the highest power of x squared and take a look at what happens. So if I divide all of this by the highest power x squared, you arrive to this conclusion. And this is what's probably going to tell us what's going on. You're going to have 1/x plus 1/x squared. And this could help. Let's see. that means, and as we go to negative infinity, of course, you still get 0. So I didn't get much out of that is the limit, but we already knew the limit 0 because of the asymptote. I'm just trying to fine tune it because what happens, the question I'm asking clearly, I should ask clearly, is does it shift when that asymptote has like the horizontal asymptote? Remember, it's the long run behavior though. I am getting to a point, right? And we could see in the original graph on the computer that it does flatten out as x goes to negative infinity. It does go to 0, right? It approaches 0, right? It still does that. But in the close short run behavior, okay, now we're learning a keystone now. So this, rational functions, and one of the good things about, and they have a lot going on because they are really used a lot in complex math. And one of the things we're learning about there's a lot you can get out of them. One of the things we're picking up now, and I'm going to get to the point, is that near the origin, things may behave a little differently. But even if it does cross, this dominating long run behavior dominates quite quickly, right? And because of that, you can have a little bit of exposure or cross exposure. You can still cross the asymptote, but not violently, right? Nothing like that. So this is really, if you put the concepts together, long run behavior and what it does, and how it is affected by short run behavior. It allows us to bend the rules. In other words, keystones can be bent. Keystone bender, and they're very rare, of course, but the keystone bender here is going to be the fact that that when you get close to it, you can cross a barrier, a horizontal asymptote specifically, right? You can cross a horizontal asymptote, but only subtly, as it is in connection to the long run behavior and the short run behavior. Because we know the long run makes it to where that starts to flatten out. Does that make sense? So as your teacher, we got a little bit of a curveball here, didn't we? I've got to admit that I made a mistake when I made the problems. There was one thing I didn't teach you, and it's this keystone bender, one of the keystone benders for the day. And that's going to be that you can't cross a horizontal asymptote. You can cross it, but only subtly. Does that make sense?
Yes.
And because of the limit, because of the long run behavior as we go to the left, that's going to squash, the behavior of the graph is going to definitely approach 0. So it's going to approach that horizontal asymptote. This is rare, but it does happen. Or I don't want to say it's rare, but it does happen. And I'd say it's less, and it's really not as, I don't want to say it's like not a big deal, but it's really not too big of a deal. But it can immediately confuse you and become a great error in thinking, and you can get confused and miss the problem and graphing it because of that. We can bend the rule a little bit. But when I say bend, when I say a little bit, I mean just a little bit. So let's move on to the topic of the day, which is going to be absolute value functions.
Anakin, Chancellor Palpatine is evil! From my point of view, the Jedi are evil. Well, then you are lost!
This is the end for you, my master. Ninja, vanish!